Please welcome to the stage Dr. Zina Jarrahi Cinker, Chief Creator of XPANSE, and joining us virtually, Sir Roger Penrose, Nobel Laureate and Emeritus Rouse Board Professor of Mathematics at the University of Oxford.
Round of applause, please. So Roger, we were having such a wonderful conversation backstage. I was thinking, we're getting to this thing too early. So I wanted to bring this conversation to our audience. And I started by telling you that thank you for writing the book, Road to Reality, because I was on a flight from Barcelona, I believe, to the US. And I had 10 hours, and I read 150 pages of that book, and that was fascinating. So Roger, one of the things that I've been waiting so long to ask you is your work with consciousness and quantum. So Roger, are they connected? Are there any links between consciousness and quantum?
Well, you see, my original entry into this subject had to do with a lecture I went to. So I went to Cambridge as a graduate student, and there were 3 courses of lecture which had nothing whatsoever to do with my study. Hello, you something's going on there. Sorry. Yes, there were 3 courses that I went to. I thought 3 years is a long time, stupid me, and I thought that I could spend some time learning about things that weren't actually on my topic of interest, which happened to be algebraic geometry. That's a pure mathematical subject, nothing to do with physics necessarily or anything like that. But one of the talks I went to was by Herman Bondi on general relativity. That was very influential to my later work, as I found out. One was by the great Paul Dirac on quantum mechanics. And the third course was about mathematical logic by a man called Steen. And I learned about computation, the idea of what you can do with computers and the limitations of what you can do with computers. And I learned about Gödel's theorem. And that really I found completely stunning. I had heard before that Gödel's theorem was something, Gödel's incompleteness theorem. There are 2 theorems, but they're more or less the same for what I want to say here. I'd learned previously, I had the idea that what they explained were that some things in mathematics that you couldn't prove. And I found this very disturbing. But when I learned what it really was, I found it amazing. Because what he shows, what Gödel shows, I should say, is that if you have a series of rules of proof, say axioms and rules of procedure, which you would, if you follow these things rigorously, that would give you a proof of some mathematical statement. So that would be, if you like, what you've decided is an official way of proving something. And what Gödel shows is that you can construct a sentence, and this is the hard part, of course. You can make the sentence say, roughly, if you know the meaning of what the sentence is, says, I am not provable by those rules. And so then you say, well, if you can make it do it, the challenge, of course, is to make it do that. But you really understand it. You can see that is what it says. That's what the mathematical statement says. I am not provable by the rules. And then you say, well, perhaps it's false. Then it is provable by the rules. And since the rules are set up to be so that if you can use them and you get truth, then it's, if the rules tell you it's true, then you believe it's true. So that means that it's true. But it's saying if it's true, then it's not provable by the rules. So I found it quite stunning. How do we know it's true? Well, we don't know it's true by using the rules. It's just said you can't do it that way. What you do is you know that it's true by virtue of your trust in the rules. What I really mean is that you know that the rules, by studying them properly, you can say, look at the first rule, say, that's okay. Look at the second rule, and you say, yes, I think so, that's all right. And then you go on like that, and you convince yourself that if anything follows those rules, it must be true. So what Gödel shows is that it's your being able to ascertain that these rules only give you truths goes beyond the use of the rules themselves. And I found that absolutely stunning. What it really tells you, to me anyway, told me, is that your understanding of what the rules actually mean and why they work is giving you more power than actually the use of the rules. You have to understand why the rules work. And then I think, what does understanding mean? Well, understanding, by its very nature, you might say, an object wouldn't be considered to understand something if it's not aware of it. So it's an element of awareness. It is to understand something, you really have to be aware of it. The word doesn't make any sense otherwise. So it's something to do with awareness. So this tells me that awareness, whatever it is, cannot be a computational thing. You see, this is the sort of Turing business. You could imagine a complicated computer which seems to behave like a human or something. And you try to ask it questions to see whether it really there's a conscious being there or not. I think it's not a bad test, actually. Some people sort of dismiss it now, but I think it isn't a bad test. If you want to know whether something is a robot or not, you just ask it various questions, and eventually it's not so hard to tell. And I think that's still true, despite where artificial intelligence has reached. If you have any extended conversation with such a device, you get pretty convinced whether there's a person there or not.
So Roger, you talk a lot about the collapse of the wave function and the link with your theory with consciousness. And I met Stuart Hemroff, I think it was a year and a half ago in Italy, and I went to Italy, to Sicily, just to meet with you. But that day, I think that you did not show up. So I was listening to you via Zoom. We had you via Zoom at the Science of Consciousness conference. And Stu was telling me about the collapse of the wave function and your theory. Can I hear it from you? What is the connection? And what is the collapse of the wave function? Not everybody here in this audience is physicists.
Well, I should continue with this story, which I've just been telling you, really. So I had to think, if our conscious understanding, and I should first say that understanding, although it requires consciousness, it's really only a small part of what consciousness does. I mean, perception of the color blue, for example, is a conscious experience, but it's quite different from the concept of understanding, certainly in the sense I'm talking about. So you might say, it's a very small part of what consciousness is. But nevertheless, it's that part which I tended to concentrate on. So what is understanding? Well, it seems to involve consciousness, as I said. So I had to think, well, if it's something which you cannot do on a computer, which the argument I was trying to make before seemed to show, that it's not a computational process, it's something else. But yet I am a physicalist in the sense that I believe what's going on in our heads is something according to the laws of physics. I don't think there's some magic that comes from the who knows where and creates consciousness, which is something quite separate from the way the physical world operates. I believe it to be something, part of the way the world operates. It's not a part that we understand yet. And I had to think of what, if it is, if it's to do with Newtonian mechanics, well, you could put that on a computer. What about Einstein's theory of general relativity? Well, you could put that on. It's not so easy, but you could still put it on a computer. What about quantum mechanics? Well, quantum mechanics has two parts to it, basically. One of them is what's called the Schrödinger equation, or unitary evolution, all sorts of words for the same thing. The Schrödinger equation, that's an equation which tells you, if you know what the quantum state is, now you have to explain what the quantum state, that's how quantum mechanics works. You have a thing called the quantum state, which is describing the world according to the theory as best you can. And then that quantum state is a mathematical structure, and the Schrödinger equation tells you how that state evolves in time. It's a very precise equation, which is confirmed in all sorts of observation, measurements and things. But it has this characteristic that it's a deterministic evolution. If you know what the state is now, and then the Schrödinger equation will tell you what the state is in 5 minutes, 10 minutes, 100 years. The trouble is, it doesn't. When I say it doesn't, at a certain point, you do what's called collapsing the wave function. The wave function is another word for the quantum state. That's really what it is. And it chugs away according to the Schrodinger equation. And then you do what's called making a measurement. You ask the state, you say, hello, state, what is your answer to this question? And when you do that, you make a measurement on the state. And then you adopt a different rule. You might say, well, you've got a measuring device, you wheel this out of the cupboard, and that measuring device should be able to be something you describe by the Schrodinger equation as well. So you've got the measuring device and the system as well. So why doesn't the whole thing behave according to the Schrodinger equation? What is measurement if it's something different from a piece of physical apparatus? So I began to worry about these things, because in quantum mechanics, people sort of don't worry about this problem. They sort of wave it away. The theory works so well, and it does. It works extraordinarily well. Certainly for small enough things or coherent enough things, it works extraordinarily well. So it seems to be very, very precise. Nevertheless, it doesn't seem to solve this problem of the measurement process. Well, this really is what one means by the collapse of the wave function. The wave function does not simply evolve according to the Schrodinger equation, or I should say not the system, but the system together with the measuring apparatus. You might say, well, that's just part of the physical world. So why doesn't that evolve according to Schrodinger's equation? The thing is, it doesn't. And that's a big puzzle to people. Now, one of the sorts of arguments that people bring in is say, well, you've got all this environment that you can't really control. You've got all the atmosphere, you've got the heated bodies and things, which information leaks out into this uncontrollable world. And that's why you get collapse of the wave function. There are lots of arguments to show why you can look at it that way, but they've got a flaw. They don't ever really have a consistent view of the way that the world is supposed to act according to quantum mechanics. So my argument was that, as various other people also believed, that something else comes in which causes the wave function to collapse. That means that the wave function stops evolving according to the Schrodinger equation, and it does A or B or C according to your measurement says, well, are you A or are you B or are you C or are you D? And it comes up with a probability, it's A, a certain probability it's B, a certain probability it might be C, or another one that is D. And certainly the wave function tells you those probabilities, but you've changed the rules. The rules are now, you don't follow this wave function as describing reality. You say, no, you've got these different alternatives and it jumps to one or the other. This is what's called the collapse of the wave function. The wave function does not evolve according to the Schrodinger equation, but it does A or B or C or D. Now, that's a big mystery. Often people try to resolve it by this sort of measurement being something to do with the environment being uncontrollable. Okay, that gets you a little way, but it doesn't really solve the problem. The problem is there in front of our faces. And so I take the argument that I was doing before, is where do we find something non-computable in the physical laws which might explain our conscious understanding? Well, it has to be in the collapse of the wave function. It can't be in Einstein's theory of general relativity or Newton's theory, or it can't be in ordinary Schrodinger equation. That's part of quantum mechanics, but as I said before, it's only half of quantum mechanics in a certain sense. The other half is the collapse of the wave function. Many quantum physicists don't believe it's a separate thing. They believe the sort of environmental decoherence argument, which, as I say, is an incomplete argument when you look at it carefully. It does not really explain the collapse of the wave function. Something out there happens which we don't have a good theory for. And that is what I'm saying has to be involved in consciousness by this rather indirect argument. So it is an indirect argument, but the argument is that it's not just that quantum mechanics is important in understanding consciousness, it's the collapse of the wave function. It's that part of quantum mechanics that we don't understand properly, which is what's involved in consciousness. You could put the Schrodinger equation onto a machine and so it's still computable. However, the collapse of the wave function, we don't know how to do it. The way we treat it in normal physics is simply by saying it's probabilities. You have probability A or B or C or D or something. It doesn't tell you which of A or B or C or D happens. And it doesn't really see when you're supposed to do that. When you're supposed to change it from following the Schrödinger equation to these alternative things that you're measuring, A, B, or C, or D. So that's a short sort of introduction to why I think consciousness is connected, not with quantum mechanics as it exists, but quantum mechanics as it might be completed when we find a theory of the collapse of the wave function.
So Roger, what is the thread between biology and collapse of wave function?
Well, you see, we don't really see it. I should explain. People often say, oh, we don't see quantum mechanics in biology or something. This is nonsense. We see it all the time. The whole of chemistry is quantum mechanical phenomena. The way that molecules, atoms fit together and so on is quantum mechanics, starting from Niels Bohr and people, studying the hydrogen atom and then complex chemical processes and so on. These are all quantum mechanical processes. So that if you're talking about biology, well, sure, it's full of quantum, full of chemistry all over the place. It's got more than chemistry. Well, biology, we don't reduce it to chemistry. It's more complicated. Anyway, I wrote my book, The Emperor's New Mind, to try and express my puzzles, basically, about that I've just been explaining to you. How is it the collapse of the wave function can have anything to do with the way the brain operates? I had no idea. I learned as much I could about neurophysiology. I learned about the different parts of the brain, the cerebrum, cerebellum, and all this kind of stuff. And I learned about nerve propagation, the Hodgkin-Huxley theory of nerve propagation, and all this stuff. And I couldn't see anywhere in any of that why the collapse of the wave function should have any role to play. See, I start writing my book, The Emperor's New Mind. The Emperor's New Mind had to do with the question about whether there's something going on that we don't want to face up to, basically. The Emperor's New Clothes, of course, the title was based on. And the thing that I argue is missing is this thing which produces consciousness, which I believe to be connected with the collapse of the wave function. And it couldn't be just nerve propagation. I came to that conclusion. And I finished the book, at least I thought I'd finished the book, and I had no answer to this question. So I sort of invented something out of my hat, which I didn't really believe. And I finished the book, slightly dishonestly. And then it got published, and I thought I might, the hope I had was that it would inspire young people to work in physics and biology and things like that. I was rather disappointed by most of the correspondence I initially got were from old retired people. These were people who had time to read my... Yes, and I was a bit disappointed by that. People like me writing to myself. Then I got this thing from Stuart Hameroff, who was intrigued by my book enough, I guess. And he said, well, evidently there's something you don't know about biology, which is important. And he explained to me microtubules, which I get lots of nutty letters from all sorts of people. I think, oh, it's not another one of those. But, well, maybe there's something in it. Actual microtubule. And so I got in touch with Stuart, and he then came over and we had a long discussion together. And we realized that there was something to collaborate on here. You see, I didn't know about microtubules. These are these little tiny tubes which are in almost all cells. I guess they're not in red blood corpuscles, I think. They are in the white ones. But you find microtubules all over the place in biology. They're very fundamental. And there are these little tubes, I found this right amazing, which have this rather symmetrical structure and with these kind of spiral characteristics as you go along the tube. And I thought this was really something very interesting. I mean, in a sense, it goes the other way because you have all these cells have microtubules in them. What's so special about consciousness But Stewart had a particular line, which I found was interesting about consciousness, which he actually, well, his job had to do with putting people to sleep reversibly. You see, he says it's not really sleep, general anesthetics. So he was interested in general anesthetics and what they do. And he was puzzled by the fact that they're all these different kind of completely unrelated, chemically unrelated, and particularly the inert gas xenon is a general anesthetic. And it's not supposed to go under proper chemical reactions at all. So he said it's not chemistry. I think he was right. I'd never heard of these things before. And I thought there's a much better chance with these microtubules that you might be able to, particularly because they were tubes and they had various characteristics related to other things that I was familiar with. And I thought there's a chance, a real chance that something might be there which could keep coherence going. You don't want to disturb the system and get too much involved with the environment, because then you lose control of the system. And if there is collapse of the wave function, it's no use to you. It just happens randomly and there's no use. But if you have it controlled in some way, like in microtubules, there's a much better chance. So that was how I got to know Stewart, yes.
So Roger, I think that me and Stuart, when we connected, it was because my field is graphene and carbon nanotubes. So yes, that's why we connected. And
yes.
how much work has been done right now? Do you guys collaborate with carbon nanotube community to see if these coherence phenomena actually happen? Are there any experiments done?
There are lots of, well, you see, I've really a bit lost track of the subject because it got too biological and I can't, you see.
Yeah, we keep jumping around.
Complicated for me. But yes, there have been recent experiments which seem to connect things with microtubules, which is quite promising. I'm not an expert on this, so I'd rather not comment on it. But can I say something about carbon nanotubes? Because it was one of the things that interested me. I'm not very up on them myself. You can explain to me perhaps. But I was aware, I read a paper where they showed me these different kinds of tubes and with different arrangements of carbon atoms, if I have it right. And some of them, you see, they're like a crystal in that you have a symmetry as you go along the tubes. But as you go along the tubes, the symmetry might involve a rotation along the tube. Now, there were particular ones where you had a symmetry which didn't have a rotation. You went straight along the tube. And my experience that I'd read in this article, and you can correct me if I have it wrong, that you could find in at least some of these, there were superconducting behavior.
Yes.
So that really hit me. And what hit me particularly was in the microtubules that you find in mammals, at least. I'm not sure if it's universal. You do find one of the symmetries is along the tube, so that it had this characteristic. You can make in the lab, you can make microtubules which have, I should say, they have 13 of these columns, 13 columns, and if you like, they repeat 5 one way and 8 the other way, or something like that. But you do have one of the symmetries is along the tube without any rotation. And this seemed to ring a bell with me of what I'd seen about carbon nanotubes, that there are these which seem to have this symmetry, which have superconducting properties when they have that symmetry. And I noticed this was a feature of microtubules. And you can make them in the lab without this. You can make them with 14 or with 12. And so there's nothing against them, chemically or biologically, them having different numbers of going this way and that way. But it just happens that the ones that you have in mammals, at least, I'm not sure how far it goes, I'm not an expert on these things, but you certainly find this in other, not just humans, in all sorts of animals, where you have these translational symmetry, which maybe have something to do with a quantum mechanical effect, which could preserve coherence because of the symmetry which other microtubules don't necessarily have. Perhaps I can
So
leave it.
Roger, does that
Yes,
mean that if we have, with the silicon-based infrastructure that we have with AI, based on your theory, we will not be able to achieve consciousness. But now we are seeing a lot of work in our conference today with biological infrastructure for computation, biocomputers that are using organoid intelligence. Do you think that if microtubules exist, which I assume that it exists in these infrastructures as well, I have to ask our experts, do you think we'll be able to actually create consciousness in biological computation?
Well, I think the trouble is the word you've just used, namely computation, is, for me, the wrong word. See, computation, as I learned from Steen in the lectures I went to in Cambridge, computation is a very specific notion, which was introduced not just by Turing. I mean, he made it popular. There were sort of Church and who are the other people? Curry, I think. There are various mathematicians before Turing got into it. And they had formulated this notion of computability. And it's known that in mathematics, there are certain problems which are not computable. And they're quite simple problems. I mean, I like to give the example of making shapes built out of square. You can have a square lattice in the plane, and you can make various shapes out of square pieces stuck together. And it's not a computable problem. So if you have a finite number of these shapes, will they tile the plane or not? That is not a problem which is computable. There is no computer, there's no computer program, if you like, which will say yes or no, given this set of tiles. And I found this very fascinating. So the notion of computability or non-computability was something quite clearly in my mind in mathematics. So you have that notion. So there are things which are not computable in mathematics. Now, whether you find them in the physical world is a separate question. And I'm trying to say, yes, you do find them in the physical world. There are things which are non-computable. They might even give you answers to things which you couldn't put on a computer, because the notion of computability is a clear-cut mathematical notion, and people don't seem to talk about it. When they talk about the power of your machine or something, how many bits or something can you do together and how long, things like that, to compute the answer to some problem. They don't face up to the fact that it's well known in pure mathematics that you have problems which don't have computable solutions.
Mm-hmm.
That doesn't matter that there's a you see, it doesn't mean that a being could do that. It doesn't mean, I mean, there's a famous problem that our mathematical institute is now named after the person who solved it, namely Andrew Wiles. The problem was formulated by Fermat, who had written in the margin of some book, I have found a very beautiful solution to this problem. It had to do with the being, you know, you can take two square numbers together and add them together and you make a third one. Sure, there are lots of examples of that. But if you take two cube numbers, add them together and make a third cube, there is no solution. How about cube fourth powers, fifth powers, sixth powers? And Fermat had written down in the margin of his book, I have found a truly remarkable proof of this result. Nobody has been able to discover this truly remarkable proof. The normal belief now is that he'd made a mistake. However, it happens to be true. And this was the work that Andrew Wiles did. And when you go into the details of his proof, it's really quite high order thing. It's not something you could imagine a simple computer doing. It could really be quite subtle, and you might have to go several layers up beyond computability. But nevertheless, it doesn't stop you solving problems. If you're clever enough, you can see ways of solving problems for which there is no algorithmic, no general solution to the problem, but nevertheless, you may be able to solve this problem or that problem. And this particular problem, which is called Fermat's last theorem, wasn't really a theorem to Fermat because he probably didn't have the answer. But anyway, Andrew Wiles does have the answer. And the answer is yes, it's true. There is no, apart from the square numbers, you can't do it.
So Roger, do you think we have a lot of material scientists, probably, a lot of carbon nanotube and graphene scientists in this crowd right now? Should they get involved in the field of consciousness and collaborate?
Well, I don't know. You see, the argument here is something a bit more you see, each one, yeah, I'm not quite sure how to say it. You see, you could, I suppose, I'm not sure. I'm talking beyond what I understand on the subject. But let me just say that the question of conscious understanding, you don't have to be Andrew Wiles to be conscious. That's certainly true. I hope not, anyway. It's not your ability to do subtle mathematics. It's something much more primitive, which is involved. And I think that goes way down in the animal kingdom. I think chimpanzees, certainly, dogs, anybody who owns a dog will think that dog is certainly conscious. Goes way down. What about an ant or a bee? I'm not sure.
Yeah.
It's a reasonable possibility that there might be something in honeybees. I mean, they do very subtle things. And when you look at them under a microscope, apparently they do. I was told that they even play football in some way with each other. Extraordinary. I'm quite prepared to believe that the phenomenon of consciousness is present in bees. I have no reason to believe one way or the other, except that maybe the football. But apart from that, it could be that they are conscious in some way, maybe not quite as developed as human beings. That's not the point. Now, what is consciousness? Well, I don't know. But what I'm trying to argue is that whatever it is, it seems to involve something beyond computable physics. And so I would try and argue that it seems to involve whatever is lying behind the collapse of the wave function, because that is something that we don't understand in physics yet. We don't really have a theory which goes beyond standard quantum mechanics to incorporate, even to say exactly when it happens. Well, there are some theories, and I have a particular idea myself, which, well, actually, a mathematician called Diósi, a Hungarian, who about 2 years earlier than I found this formula, he found it first. He didn't have the same argument that I had, but the argument was to have a look at the conflict between the two great theories of 20th century physics, namely Einstein's general theory of relativity and the theory of quantum mechanics, which had many, many contributors to. Now, these two theories have not been brought together in current physics. People usually say we haven't yet been able to quantize gravity. What they say is applying the rules of quantum mechanics to general relativity. To me, that's the wrong way around. Not that it's wrong. No. Quantizing gravity is part of the story. I'm sure that's correct. But it's not the important part of the theory. The important part of the theory is the other way around. How to solve this fundamental problem of quantum mechanics, which is the collapse of the wave function. We don't have a theory which tells you how the wave function collapses, even when it collapses. But by combining the ideas of general relativity and quantum mechanics together, you can get an estimate of the time scale. How long will a system last before it collapses? And there has a formula which was originally due to Diósi, who was this Hungarian physicist, and I obtained independently the same formula that he had, where you can work out for a superposition. If I have an object here and an object here, then I can work out, if I put it in the superposition of here and here, how long will it take to become either here or here? For this object, it would be a ridiculously tiny fraction of a second. If it's a carbon atom, it would be longer than the current age of the universe from the Big Bang to now, much longer. So you have to see a theory which probes the intermediate region of where quantum mechanics starts to go wrong, as I say, where the collapse starts to enter into the situation, and you need a broadened theory which goes beyond current quantum mechanics. And I am claiming, as I've just been saying, that whatever is going on in our brains with consciousness, it involves that broader theory, which we don't have, but we have some inkling as to where it is. Do we see anything in the activities of the brain which could be at the level where you might see the collapse of the wave function coming in? And when I say the brain, you see, we have to be careful because there is the cerebrum, this part sort of the top, people usually think of when they think of the brain. There's the cerebellum. Now, there are more neurons in the cerebellum than there are in the cerebrum. That part is behind and underneath. However, as far as we know, it's entirely unconscious. It does things completely unconsciously, as far as we can tell. And then you look at the cells and you find, well, they're pretty well the same, but they're organized maybe in a different way. Stewart claims that there are certain cells called pyramidal cells, which are not found in the cerebellum. And he argues from this reason that they could well be, or maybe other reasons too, that they could well be the clue to where consciousness comes in the activities of the cerebrum. So the cerebrum, I'm not saying that everything that goes on there is conscious. It seems to be that it's not. I mean, there's some subtle things going on, and they may be collective. They may not be localized in any particular spot. It's a really interesting question. But Stewart takes the view that they are primarily, the activity is in these pyramidal cells. He has good reasons for thinking that. I think it's an interesting idea, and it could possibly be really a clue to what's really going on.
Thank you so much, Sir Roger. I wish I had an hour to sit down and talk to you and ask you questions. I truly appreciate it. It was an honor, truly, for me. Thank you so much for spending the time with us and with our audience and sharing your knowledge and your wisdom. Thank you so much.